So just a quick introduction. ProtaStructure is a structural engineering design software that designs concrete and steel structures. So I currently have the student version. If you're interested in ProtaStructure trial, I can put the link in the description for you. So this is the interface I'm met with. So I'll create a new project. So already loaded, there are numerous design codes in the software. You can see, but here we practice in Nigeria, so I'm going to go with the BS code, UK BS code. Then I press OK. Sorry, I have to put the name, so let's just say YouTube project. Then I click on OK. Then we're met with this interface. So you can see a grid line, a y coordinate, x coordinate. So this is the environment we're going to work on. This is the plan view. You can see at story 1 plan. So this is the structure tree. Basically all the structural elements that are going to model are going to be accessible through the structure tree. So by default it creates a story, two stories, story 0 and story 1. Story 0 is your foundation level, while story 1 is your first suspended floor. So this plan view is the plan view of your first suspended floor. So if you have a bungalow, for instance, story 1 would be your roof beam and story 0 will be your foundation. So you get me? Story building, your story 1 will be your first floor, then your story 2 will be your roof beam. So you get me? So that's how it works. So this is the environment. So if we look at the ribbon over here, we work from the left to the right. So first of all, you're going to have a reference drawing. So as a structural engineer, you're going to produce a scheme on AutoCAD or Revit. So from Revit or AutoCAD, you can import your scheme to ProtaStructure, and the software would help you would help you and the software would allow you work with the scheme you've already created on Revit and Prota, preventing you from redoing the whole scheme again on ProtaStructure. But currently, I don't have a external reference drawing. I'm just working directly from Prota. Just want to show you a quick demonstration of how the software works. So I go to my modeling tab. So just like I said, you work from the left to the right. You get. So you model your grids. When you model your grids, you model your column. When you model your columns, you model your walls. When you model your walls, you model your beams. When you model your beams, you model your slabs. And if your slabs have opening, you put the opening. Then you label this is for starting slab, this is for setting the slab types. So the same applies to steel members. When you label your column, you label your frame. Your frame is your beam and your columns in steel. Then you label these trusses. Then you can define support types. In structural engineering we have fixed, pin, and roller. So fixed, the movement is restricted. The pin, you can rotate about x-axis, and the ruler you can rotate about x and y-axis. You can see. But since we're going to have a rigid structure, I'm going to keep it as fixed because it's going to be casting suit. So I'm not just going to work with that. So we have floor plan sections just to show sections through the floor to show different beam depths or hidden details that would not be shown in the plan. Then we have plane definition. If you want to change the work plane, you know, every not every structural element is going to be on the same plane. There are some that are going to be slanted. So when a member is slanted, it's going to be on a different plane compared to a member that is horizontal or vertical. So the software models horizontal and vertical members. But in case you need a slanted member like a ramp, you need to define a plane for it. So I'll just click on orthogonal axis generator and I'll click here. So direction 1 axis. So direction 1 axis is the horizontal axis. So the axis label starts from A automatically. The step is 1. If I change the step to 2, the next axis is going to be C. So this axis spacing, meaning what should be the spacing between the axes? So 5,000 times 3 means it's going to create 3 axes of 5,000 center to center. You get me? So I'm just going to leave this to 5,000 times 2 because I'm trying to do a small project. So A1, so this is direction 2 is your horizontal axis. So I'm going to change this to like 5,000 by 2 2. So I'm just going to click OK. So the same applies to it. So you can see A 5 meter, 5 meter, 5 meter, 5 meter. Exactly. So we have our grid lines. So what next? You model your columns. So I like to choose 450 by 230. Or we could also start with 230 by 230 to see how that behaves. Then depending on how it behaves, then we could always reinforce it to see how it behaves. Sorry, we could always so we could start with 230 by 230 columns. Then depending on the results of the analysis, that will determine if we're going to increase the section or not. So that's what I meant to say. So I don't want to have shear walls here. I'm just going to model normal beams. So I just want my beam to be 230 width and 450 depth. I want it to be on the center. So you could just do like this, open the box, then like this. So for your slab, to model your slab, you need to define a load case in Prota. So that's what it's telling me. So I just do a load generator. So what this means is equal to sign means the span is loaded. The normal underscore is not loaded. Span loaded, not loaded. So it's just a way of analyzing the structure in different scenarios, different load conditions. So the more you select it, the more condition it actually provides. You get me? So all these use crack sections, they are for earthquake, seismic design. So I'm just going to leave that like that now. So I'm just going to press OK and generate the load. So you can see we have this load G and Q. So I also want to create another load combination. So I'll rename this as ultimate limit state. Yeah, add another load combination. I want to add another load combination. So it duplicates that, but I want it to be service limit state. So the service load is 1, has a load factor of 1.0 according to the code standard. So I press OK, and it allows me to start the slab. So I want to start with the slab of 150 thickness, which is a 6-inch slab. Coming over of 20. I want it to be placed at the beam regions. And the load, I just want a room load, and imposed load of 1.5 because it's a domestic area. I'm not having any slow load on the structure. It's not a roof, so I'm not having any roof load. So if you click, you see slab does not contribute to floor diaphragm. This is a slab will not contribute to the floor diaphragm only in a flat slab system. Floor diaphragms are used to resist horizontal loads. So when there's a slab beam connection, the slab will resist horizontal load because of the beam. So in our case, the slab contributes to the floor diaphragm. So that's why I'm leaving it unchecked. So I'll put that there, put this there, put this there. So I go to the loading tabs. I want to define wall loads. Assume what our walls have certain load. So I'll just edit load here. Then I'll select the member. I'll define a wall load. So you could define a wall in your library. But right now I'll not do that. I just want to use a user define wall load. So let's just use the default here and just insert it. Then pick members. Then you just press OK. And that's how you have your wall load. Now you can see the wall load is not covering the width of this beam. So I have to rectify that. So I just edit wall load. Edit wall load. Now this wall load, I just edit it. So you can see we have and we have a 230 beam. So I just update it. So I just want it to be evenly distributed on the beam. So I'll copy wall load. Okay. Then I paste the wall load. So this is the plan level. This is the plan view rather. So I can create a 3D view just to show you a 3D view just to show you what we've done so far. So we have this building with this is the ground floor, this is the ground floor, this is the first suspended floor, and we have some walls on it. So let's create another. So why remember I told you in the beginning of the video, we have a 1-story building. We're going to have 2 stories or 3 rather. That's story 0, story 1, and story 2. So since we have if a since we do have a 1-story building right now, what we can do is we'll just go here, insert story. So we start the maximum number of stories we're going to have, that's 2. Okay. Yes, it creates another story. So because the story is similar, because we're just going to have a beam above, we're not going to have a floor, so the frame is similar. So I could just import the columns and the beams to that level, or neglecting the slab because there's going to be a roof there. So the roof beam is just it's not carrying a slab, except if there's an architectural requirement where there's a slab supporting a tank or so. But in this scenario, I'm assuming that the roof beam is just carrying a self weight, so I'm not loading the roof beam. So design is based on the condition, but in reality, roof beam is not just going to carry self weight. It's going to carry the roof and other environmental loads you get, like snow, depending on your region, it's going to carry rain. So yeah. So generate story from story one, target story two, select the select. So I just want the columns and the beams. I press OK. So I would remove the loads because I don't have any walls on my roof. So you can filter selection, just want to select views, just delete loads, and here we have it on 3D. So this is what we have on 3D. So now you can see now that we've loaded the structure now you see it's a load composition by FE. Now we're not going to use it because we don't have complex loading on the structure. You only need finite element when the loadings on the structure exceeds the limit of the yield line method. So the yield line method of analysis for slabs and finite element method of analysis of slabs frames. Yield line for slabs, finite element for slabs and frames. You get. So the yield line, what it does is it converts your slab loads to yield lines. So which is what you can see here. It shows the load distribution by yield lines depending on the aspect ratio of the slab. So we have one-way slabs and two-way slabs. So all these are modeled at two-way slabs. That's why you can see the load distribution pattern is even in all the slabs. So not that load distribution is even in all two-way slabs, but this is a square. That's why it feels that way. So the condition for two-way is if the longer span of a slab and the shorter span, if the when you do ly, which is longer span, you divide it by your shorter span. If you get a value less than or equal to 2, you consider it a two-way slab. If it is greater, you consider it a one-way slab. So that's just the condition. So U-line method is the default load transfer method. So basically it transfers the load to the slab. So what this load composition by FE does, it calculates the load. You can see calculates and distributes the slab load onto the beam. That's just what it does. It just calculates the load and distributes it. But we're not going to use that now. So we go to review. So you do a boolean model check before you start your analysis. Check if we have any errors. You can see we have 2 errors. Beam 1B5 and 1.8 are overlapping. Okay. 1B5 and 2B8. 1B5. Okay, yeah. Exactly. Must have made a mistake when I was measuring it. So it's here too. Okay. So you see, you have to like check for errors before you proceed. You can't just proceed while you are getting errors from the software because you don't know what those errors mean. So what I like to do is I also like to purge unused sections to then probably delete unused axis. I don't have any unused axis. And I'll relabel the members because of my presentation. So columns left to choose this, then columns and slabs rather. Press OK. Then retain compatible layers between story. What this means is if you have a column 1C1 and you have another column above it, is going to retain it to 2C1. If you have a transfer column which is not supported by the column below, it's going to give it its own label. So press OK. So I want to retain the level. And for my beams, I want the same thing in this project because all the beams are similar. So you can see this 2B1. If you go down, the beam there is 1B1. So that's review. So you load, you review, then you analyze. So there are two types of analysis. There's FE analysis and building analysis. The FE analysis is to analyze the FE flow analysis is to analyze a floor slab, just like I mentioned. To analyze the floor slab using finite element method. You analyze the floor slab, it shows you how the load behaves, how this load causes the slab to deform rather. Shows you how the load causes the slab to deform, shows you the shear force and bending, deflection of slabs, and compares it to the limits of the code. So I'm going to do an FE analysis first. I'm going to select all to cater for cracking and creep. So cracking is a thing of shrinkage. You will get cracks due to shrinkage or under reinforcement and excessive loading. There are a lot of reasons, settlement, a lot of reasons why you could get crack and unexpected loading too. So creep is the effect of long-term loading. I want to know the structure, how it will behave in over like a long time. So to kind of like give you that kind of estimate, you need to like reduce the stiffness of the structure based on the loading you've put on the structure to give you a more conservative design. So I'm just going to input my loads here. So for average dead load, I think I have 2.5 and average live load 1.5. So this is a stiffness factor to apply to cater for long-term effect of my structural elements. But now the effects are really the elements that really would that I'm most concerned with is the element I'm most concerned with is the slab because the work carries the people, you know. My frame, as long as my frame as long as my frames are the right sections, when I mean frame, I mean the beams and the columns, there's nothing going to happen to it. I just say it like that. So this is the factor. I just want to apply it to the slabs. I don't have any walls. So I do an FE floor mesh analysis. And I light load. And analysis complete. So you just list the storage placement so you can see it's not really that much. So this is telling you 1, 2, 3. That's 10 mm. It's less than an inch. So you can't even see the displacement, which is fine. So you close. So I've analyzed the floors. So I could just go on and design the floors like this. I could go on and design the floors. But I want to analyze the whole frame because the I want to go and analyze the whole frame. So you set all your parameters. I'll use the default ones, model option, everything. Just leave it as default for now. If you don't build the model check, I'll just go to analysis straight up. I'm not designing, I'm just analyzing. So it satisfies the limits, and then you check your load comparison report. So you compare the value here on the slab to the one decomposed, the value here to the one decomposed. These values should not exceed 5%, or the software will yield a warning which is in the settings already. It's tolerance 5%. You get. So it's a standard we use in the design. So my major concern is post analysis results. So I'll just go to display analytical model to see how our structure behaves. So I just remove this cubic core because it over exaggerates the deflection. So if I animate it, you can see on our dead load just the weight of the structure. This is how the structure behaves. But I want to see on service load, and this is the worst case scenario. Usually it is, but there are some cases where, so based on the combination, a member may not have the worst case combination from the ULS, might be from one of these nodal loads. So I just pause the animation, then you can see review your axial load. This is your N is your axial load for the columns. See the axial load of the columns. Yeah. Axial load of the columns ensures that it increases as it goes down. We have torsion for the beam and slab column and beam connection. So I did not include effect of torsion. And this is your shear force for your beams. Ensure that shear force is maximum at support for simply supported connections. This is the bending moment for the columns. The column is a fixed column. So that's why explains the connection like this. This is the bending moment for the shear force. For the beams rather. Bending moment for the beams. And this is the shear force for the columns. So that's that. You go through the analysis results and you understand and ensure that the building actually behaves in a way you've predicted before you carry on with your design. So in respect to slabs, I'll go to the flow analysis, post analysis result. I'll go to display analytical model. So you can see my slabs here. So for slabs, I really just like to go to the plan view to see how things are there. Views. So let's go to the plan view.